Welcome back to Visionary Tech and to our course on microprocessors and microcontrollers in Mechatronic Control Systems. In the last lesson, we explored the architecture of microprocessors and how the different sections like the CPU, memory, and I/O units are organized. In this video, we're going to take the next step and look at how these sections actually communicate with each other. The answer lies in something fundamental to all computer systems: the bus. In a microprocessor-based system, the different components, such as the CPU, memory, and input-output devices, need a way to communicate with each other. This communication happens through shared electrical pathways called buses. Now, what exactly is a bus? Physically, a bus is a collection of parallel conductors, in other words, wires that run side by side. These wires can carry digital signals in the form of binary values, ones and zeros. The bus provides a common communication highway that all the chips in the system can use. If we tried to connect each chip with every other chip individually, the number of wires would explode and the circuit would become unmanageable. Imagine connecting 10 people in a room so that each person has a separate telephone line to everyone else. It would be a mess of wires. Instead, using a shared bus is like giving everyone access to the same telephone network. Each person can take turns talking. Of course, this also means that only one device can use the bus at a time. If the CPU is sending data to memory, other devices must wait until that transfer is finished. This process of taking turns is controlled by timing signals and control logic. Buses usually come in parallel form with multiple conductors carrying multiple bits at the same time. For example, a 16-line bus can transmit a 16-bit word in one go. This is much faster than serial transmission, where the same word would have to be sent bit by bit over a single wire. Now let's look at the three main types of buses in a microprocessor system.
The data bus. The data bus is responsible for carrying the actual information being processed. It links the CPU to memory and to input-output devices. Each line of the data bus carries one bit of a binary word. For example, a 4-bit data bus could carry the binary number 1010, each digit being transmitted on a separate wire at the same time. The width of the data bus, meaning the number of lines, determines how large the words can be. A 4-bit data bus can represent 16 different values, from 0 to 15. Early microprocessors like the Intel 4004 used 4-bit buses, and these are still found today in small controllers inside toys and appliances. As technology advanced, microprocessors grew to 8-bit, 16-bit, 32-bit, and now even 64-bit buses. The wider the data bus, the more information can be moved per clock cycle, and the more powerful the processor can become.
2. The address bus. While the data bus carries the information itself, the address bus carries the information about where that data should go. Every memory cell inside RAM or ROM has its own unique identification number, called an address. The CPU places an address on the address bus to tell the system which location it wants to read from or write to. Similarly, every input and output port also has an address. The width of the address bus determines how many locations can be accessed. With an 8-bit address bus, we can select 2 to the 8th, or 256 memory locations. With a 16-bit address bus, the system can select 2 to the 16th locations. That's 65,536, commonly referred to as 64K. With a 32-bit address bus, we jump to over 4 billion locations, which is why 32-bit processors can handle large amounts of memory. This is a key factor in system performance. The wider the address bus, the more memory and I/O devices the CPU can work with. 3. The control bus. The third type is the control bus. This bus doesn't carry data or addresses. Instead, it carries the signals that manage and coordinate the system's operations. For example, the CPU needs to tell memory whether it intends to read from it or write to it. These actions are represented by control signals, read and write. Other control signals might include interrupts, reset commands, or device select signals. The control bus also carries the system clock signal. This is generated by a crystal oscillator and provides a regular series of pulses to synchronize all the actions in the system. Without this clock, the CPU, memory, and I/O devices would not know when to act or when to wait. So, to summarize, the data bus moves the information itself. The address bus specifies where that information should come from or go to, and the control bus carries the instructions and timing signals that keep the whole system in order. Together, these three buses form the communication backbone of a microprocessor system. Without them, the CPU would be isolated and unable to interact with memory or with the outside world. Understanding buses is essential because they define how fast data can move, how much memory can be accessed, and how smoothly the processor coordinates all its tasks. In the next video, we'll dive deeper into the central processing unit itself, breaking down its key components and learning how instructions are executed step by step. Thanks for watching Visionary Tech. Don't forget to subscribe and continue the journey with us in the next lesson.